So discrete optimization, again, linear programming part 2. Okay, so this is getting really exciting now. Okay, so what we saw last time was the geometric view of linear programming. And what we're going to do now is do the connection between this geometric view and the algebraic view. Okay, so we're going to link the two, and this is where this thing is really nice. Okay, so remember what we saw last time is that we could solve this problem from a geometry standpoint by simply looking at all the vertices and taking the one which has the best value for the objective function. Okay, of course, it's like, oh, how do I get these vertices? It's like, hey, it's crazy, right? Writing an algorithm to get these vertices doesn't seem so simple. Okay, we can do that by hand, but how do we do that, on a computer? And that's the key point here. Okay, so the simplex algorithm is essentially an intelligent way of actually exploring these vertices. And as I told you, this is where the connection between the geometry and the algebraic view is really interesting. Okay, so once again, I told you that this algorithm was invented by George Dantzig. And one of the things you have to understand is that this algorithm is actually still, after like 65 years. Actually, wow, this is 65 years. After 65 years, is still a complete enigma, right? It works incredibly well in practice, always solving this problem really fast in general. But it has an exponential worst case. So in the worst case, it's terrible, right? But this worst case doesn't seem to happen, in almost never, okay? So you can construct example where it will happen, but they don't seem to happen in practice. So from a theoretical standpoint, nobody really understands why this is the case, and there are really some very nice theoretical issues which are very simply stated that nobody knows the answer to. Okay, so very interesting algorithm. And so what I'm going to do today is to actually try to present this thing in an intuitive way, what the simplex algorithm do. And so this is the way I would, I could characterize this algorithm. Okay, it's very simple, right? So what you want to do is to be on top of the world. Okay, so that's the goal. Okay, the goal is to be on top of the world. Now, I'm going to give you 5 facts, okay, that will allow you to be on top of the world. Okay? The first fact that I'm going to give you is that the top of the world is the top of a mountain. Okay? Basic fact, right? Now, the second fact is the most interesting one. Okay? So the top of a mountain is a beautiful, fantastic spot. Okay? We're going to talk about beautiful, fantastic spot all the time, and I call these guys BFS. Okay? So beautiful, fantastic spot. Okay? So you have to know, okay, that the top of the world is at the top of a mountain, and the top of a mountain is a beautiful, fantastic spot. Okay? Now, the third thing that I'm going to tell you, okay, third fact, okay, is that you can move from a beautiful, fantastic point to a neighboring beautiful, fantastic spot. That's easy to do, okay? You are at the beautiful, fantastic point. You see another one, you can move there, okay? So, and then the fourth fact is that, and this is important, when you are at the top of the world, you know you are at the top of the world, okay? Fact 4. Okay? And then the last fact is that if you are at a beautiful, fantastic spot, there will always be an opportunity to move to a higher, beautiful, fantastic spot. Okay? So if you understand these 5 points, okay, so you understand linear programming. Okay? So this is as simple as that. Okay? You know that the top of the world is the top of a mountain. You know that the top of a mountain is a beautiful, fantastic spot, that you can move from beautiful, fantastic point to another neighboring beautiful, fantastic point. When you are on top of the world, you know it. Okay? And then every time you are at a beautiful, fantastic spot, there is a way for you to go to a higher, beautiful, fantastic spot. Now, so this is too simple, right? So and we have to make it complicated, and that's what I'm going to do. Okay, I'm going to do on the next slide. Okay, I'm going to take these facts and make them a little bit more complicated. Okay, because otherwise people would say what you do in science is too easy. I mean, we are not the only one to do that, right? So a doctor would talk about the distal part of your fibula. What is that, right? So can't they say this is the part of your fibula next to your ankle? No, they would say beautifully, the distal part of your fibula is the problem, right? Anyway, so lawyers are the same, right? So when you buy a house in the US, they would write things like expected performance. And you say, wow, what is this expected performance? That just means you have to buy the house, okay? But, so we're going to do the same. We're going to take this very simple algorithm and make it look complicated, such that people believe we are really clever, okay? So this is what we're going to do, okay? So we instead of saying we want to be on top of the world, we want to solve a linear program, okay? Fact number 1, what I told you is that the top of the world is at the top of the mountain. That's basically telling you that the optimal solution is located at a vertex. So when you think of a vertex, think the top of a mountain, right? Now, a vertex, okay, is actually a beautiful, fantastic spot. But we can't talk about beautiful, fantastic spot. So we're going to say it's a basic feasible solution, okay? But let's say BFS. You can think BFS, basic feasible solution, or beautiful, fantastic spot, okay? And then the three other facts are going to be essentially the same because we are talking about BFSs, right? So you can move from a BFS to another one, beautiful, fantastic spot to a beautiful, fantastic spot, or basic feasible solution to another basic feasible solution. You know that you can detect if a beautiful, fantastic spot is at the top of the world, okay? You can detect if the basic feasible solution is optimal. And then you can move from any BFS to another BFS which has a better cost, okay? Smaller cost if you minimize, higher cost if you maximize. Okay, so this is once again a little bit more complicated. No, we are talking about this basic feasible solution that we don't really know what they are, but this is the same thing as what I've shown you on the previous slide. Okay, but this is the simplex algorithm. And so what I'm going to do in the lecture is going through these various facts and explaining how they work. Okay. So we know what a linear program is, right? So minimizing this linear function and then these constraints, okay? And all the variables have to be greater than 0. We'll come back to that. This is an important part, okay? So let's back up a little bit, okay? I'm backing up, okay, right? And so what we are looking at here, first, we have a system of linear equations and we want to solve it. How do we do that? Okay, go back to high school. That's what we did, right? And so essentially what you do is you perform, Gaussian elimination to actually solve a system of linear equations like that, right? So you basically express some of the variables in terms of the other ones, okay? And so you basically isolate a bunch of variables, x1 to xm, okay? And you express them in terms of the other variables, okay? And so this is basically what we call a basic solution, okay? The variable, on the left side, okay, are going to be called the basic variables. Sometimes we tell that they are the basis, right? So, but they are the basic variable, okay? And we're going to love these guys, okay? You'll see why. And then the other variables are called the non-basic variables, okay? They are the guys that we don't really care about, okay? And then, of course, you have the b's, which are the values that we're going to give to the basic variables, okay? So this is a basic solution. Why? Because essentially, we're going to take the basic variables that you see there. We're going to give them as values the b's, okay? And then we're going to take the basic variable, the non-basic variables, and we're going to give them all zeros, okay? And if we do that, obviously these equations are going to be satisfied, right? I'm basically saying xi is equal to b, x1 is equal to b1, xm is equal to bm, and all these guys are 0. So these equations are obviously satisfied. Okay, so this is a basic solution. Okay, so I'm basically taking all the xi, giving them the bi. I'm taking in all the non-basic variables, assigning them to 0. So in a sense, think about this. In this system of equation, there are a bunch of variables that are all zeros, and that happens all the time in linear programming, right? So you will have a massive amount of variables typically assigned to 0, and then these beautiful basic variables are going to be assigned the bi's that you see there. Okay, so that's a basic solution. Okay, we'll talk about basic solution. Now, remember a beautiful, fantastic post and this F in there, right? So this is feasible or fantastic. Okay, so you're going to be fantastic or feasible when you satisfy these constraints. Okay, so you have to make sure that all the variables here, okay, have to be greater than 0. Okay, and so how do you do that? Well, for the non-basic variables, it's easy, right? So all these guys are already 0, but you want to make sure that these guys are assigned non-negative values, okay? And so that means testing when you actually isolate the x1 to xm that these guys are actually non-negative, okay? And if they are non-negative, what you have is a beautiful, fantastic spot. You have a basic feasible solution, okay? So that's what you have here. Okay, so a basic feasible solution is a solution where you isolate some of the variable, x1 to xm. It can be any one of these variables, right? So they are called the basic variables. They are assigned these b's that that you have, and all the non-basic variables which are there are assigned to 0. Okay, basic feasible solution. Okay. You're going to say, why is this guy actually obsessed with this? And you'll see why in a moment. Okay? So how do we find a beautiful, fantastic spot? We select m variables. Okay? So there will be the basic variables. We re-express them in terms of the other ones. Okay? Not in terms of each other, right? Only in terms of the non-basic variables. Okay? We can do that easily by performing Gaussian elimination. Okay? And now if all the b's are non-negative, we know that we have a basic feasible solution. Okay? So You're going to tell me, yeah, but you are dealing with equations now. But in my simplex algorithm, I have inequalities, right? So what are we going to do? Well, there is a very simple thing that you can do, okay? If you have a set of inequalities like this, okay, what you can do is always you can add some new variables, okay, S1 to Sm, okay, and transform these inequalities into equations, okay? So these S1 to Sn will have to be greater or equal to 0, okay? So you add them, there is 1 for every one of the constraints, okay? They are all forced to be greater than 0, and we call these guys the slack variables, okay? And the intuition here is very simple, right? So look at this expression that you have there, okay? So they will have a value when you assign the basic variables, okay? And then there will be the value of the b's, okay? So typically they have to be smaller or equal to that. So either they are equal, in which case the slack variable is going to be 0, otherwise the slack variable is going to be the difference between the b and then the left-hand side, okay? So essentially they are transforming this inequality, okay? They are transforming these inequalities into equation by picking up the slack and really having a variable capturing that slack. Okay, so very simple, right? So if you have a linear program with inequalities, you can transform these inequalities to equations, and that's what we want to do when we are actually implementing this method on a computer, right? Okay, so once again, to summarize, you start with your linear programs, you take all these inequalities, okay, you add slack variables and you have equations, okay, and now you select m variables, okay, so these are going to be the basic variables, you re-express them in terms of the non-basic variable, performing Gaussian elimination, and then if all the b's are non-negative, you have a basic feasible solution. You have a beautiful, fantastic spot, okay? So now, this is the key point, okay? This is the most important facts that you need to know. A vertex in the geometrical sense that I've shown you in the last lecture is actually a beautiful, fantastic spot. It's a basic feasible solution, okay? So in a sense, now we have a beautiful algorithm. I'm giving you an algorithm, right, that you can actually code on a computer, right? So the naive algorithm that we have now is that we just want to look at all the vertices. Okay, but the vertices are basic feasible solutions. So you can just enumerate all these basic feasible solutions and then take the one which is best. So you generate all the basic feasible solutions. How do you do that? Well, that's just what I explained to you, right? You isolate m variables, you express them in terms of the non-basic variables, okay? And then you perform Gaussian elimination, and then you can test if this is feasible. If it is feasible, you have a basic feasible solution, okay? So I have now this, naive algorithm that you can implement on a computer, which basically generate all these, basic feasible solution, and for every one of them, you can compute the value of the objective function, obviously. You essentially plug the values that are in that solution, okay? And then you select the one which has the best cost. Now, how many of these? Well, that's the issue, right? So there will be a very large number of them, right? It's like picking up m variables inside the m, and you want to explore all these combinations, okay? So there are many of them, okay? And so in practice, the naive algorithm that I'm showing you here is not going to work, nicely from a computational standpoint, from a performance standpoint. But we'll see how to improve it, in the next lecture, okay? So basically, summarizing what we have seen, okay? So what you want to do, okay, is to be on top of the world, which is basically a vertex, okay? And what you can do to get to, and a vertex is a basic feasible solution, and getting a basic feasible solutions is actually pretty easy. It basically consists in isolating m variables, okay, expressing them in terms of the other one, and testing if the value that you assign to them is actually non-negative, okay? We'll see a more clever way of actually exploring all these vertices, basically basic feasible solutions, next time. Thank you very much.